Let's talk about planes. At the end of our last video, we talked briefly about that idea of a plane. So that's a two-dimensional surface that extends in two directions, rather than the lines we've talked about previously, which only extend in in two directions, but in one dimension. So let's define here, what kind of planes are we talking about? A plane is a flat surface that extends infinitely in all directions. Obviously, we cannot draw an infinitely large object on a finite piece of paper or in a finite amount of time. So, we sketch it with edges like a little piece of paper, but in actuality, it's extending in every direction forever. Once again, similar to what we do with lines, while our vectors have ends, going from point A to point B, when we define a line on a graph, it extends to the right forever and the left forever. We just don't show that because it's, not really possible. So we just have a brief representation, and we just have the implicit understanding that it goes farther. We are not talking about the airplane kind of plane, so this is not what we'll be talking about in this lesson. So you'll recall that a line is just a one-dimensional object in space, and it may be described using a point on a line in a single direction vector. It naturally follows that a plane, a two-dimensional object, can be described using a point in the plane and two direction vectors. However, recall that two collinear vectors lie on and describe the same line. Thus, the two direction vectors describing the plane must be non-collinear. So remember, our one-dimensional line, we can have a point, and then our direction vector m, and then we just have scalar multiples of that to head in whatever amount or in whatever direction we need to go from the point. However, now we're talking about a plane, so we're going to have our plane, our two-dimensional surface. We'll have some point, and we'll have two direction vectors. So if I have direction vector m1 and direction vector m2, I can define any point on the plane as a combination of those vectors. So if I want to reach this point here, I'm going to extend my m1 a little bit, so I'll have multiples of m1, and then I need to move over, I'll have some multiple of m2, and that'll get me where I need to go. So we'll just briefly say like k times m1 gets us here, and I don't know, p times m2 gets us here. Whatever combination we need. We'll get into that as we go. Remember, what does it mean if vectors are collinear? What do we know about collinear vectors? Well, if they're the same line, they're going to have the same slope, or, in three dimensions, as we talk about things in terms of vectors now, they're going to have the same direction vector. So if I need lines that are not collinear, they have to be not parallel. And remember, not parallel means not having the same direction vector, or at least the direction vectors cannot be scalar multiples of each other. So vector m1 cannot equal a scalar multiple of vector m2. Next, we have a question to consider to help our understanding, and it's not in this copy of the notes, so I'll just type it in real quick. And the question we want to ask ourselves and help our understanding of planes is, true or false, any 3 points can be used to define a plane? Well, in order to prove something, we need to prove it in general terms, or we can find a single counterexample. So I'll actually tell you right now, well, you can think about it for a moment. So if you want, you can pause the video and consider what you know about planes and what you think you know to be true. And then I'll tell you the answer. And the answer is going to be false. Why? Let's find out using a counterexample. So what if all my points look like this? So I have my plane. Let's take a look at our example, and let's suppose we have our plane. I have my 3 points, and I find my direction vectors between them. And I sketch my direction vector. Okay, cool. I connect those points. We can call that M1. I can connect these points. We can call that direction vector M2. Maybe we decided to, connect these points directly, M3. We have a problem here. Do you know what it is? The problem is that all these direction vectors are collinear. So let's make a little note of that. My direction vectors are collinear, which we just said is not allowed, cannot be used to define our plane if the 3 points are collinear. So if they're all in a straight line, that's a problem. However, if they are not collinear, and I think I showed this already I showed this already up top. If I have my point and my direction vector m1 and my direction vector m2, I can define any point on the plane in terms of those direction vectors because they are not collinear. So let's make a quick note of that. So we'll notice that only 3 non-collinear points define a plane. And I noticed technically I only drew 1 point on there, so let me just indicate the points, not just the vectors, since that is the main focus of our discussion at the moment right here. All right, let's take a look at our mathematical definition of planes. As we can see here, a plane is defined in a similar way to a line. We start with a point and then add any linear combination of two vectors called basis vectors that are also in the plane. So these are like our direction vectors for our line, except there's going to be 2 of them, which we talked about a few moments ago. And we'll just note here in our diagram here, let's zoom in a little bit. We have P naught, our generic point. We have P, our specific point. We use the pi symbol to represent that we're dealing with a plane, and then we can see the direction vectors or our basis vectors here labeled B and A. And like we talked earlier, we can use those, any combination of those, to move around our plane. Continuing on, mathematical definition of planes. This is the vector form of a plane. So it should look a little familiar. So, you know, we got our vector notation or whatever. We have our position, we have our parameter and a direction vector. And like we just said, we have to be able to move in 2 different directions. One direction vector isn't enough. So you have our basis vector, so the second one is here, and a second parameter is there. Because remember, we're finding scalar multiples of 2 different vectors, so we need more than one. To find specific points on the plane, we substitute in different values for s and t. And the parametric form is the components of the vector form. So just like before, we're just going to break it down into pieces. And we'll see that in a few moments. If we take any 2 non-collinear vectors in the plane, so that's my m1 and m2. And remember we said earlier that m1 and m2 can be any 2 vectors as long as they are not collinear. That is to say, they are not the same or they are not scalar multiples of each other. Then any arbitrary vector in the plane, such as p naught p, so going from our specific point, going from our generic point to our specific point, p naught to p, can be expressed as a vector sum of scalar multiples of these 2 vectors. So we can add up some combination of these vectors, and we can even see that here briefly, that if I start at p naught, and I have vector b, and maybe I need a little bit more of vector b, so I'll have some scalar multiple. And we can see down here my vector a. Well, I can just add that to the end of my vector b, however many times I've multiplied it, and end up at point p. So I can see here that the vector p naught to p can be thought up as a sum of my b vector, scaled however it needed to be scaled, or whatever linear or scalar combination of that vector, and then my vector a, once again, whatever scalar multiple of vector a I needed. So some multiple of vector b, some multiple of vector b, and some multiple of vector a. So we let A and B be two such vectors in the plane, so any two non-collinear vectors, such that SA plus TB gives us the vector P naught to P. For some, S and T are an element of the real as shown in the diagram. So once again, we need to define our parameter. We need to state what possible values can it have. And here we're saying that S and T can be all real values. There's no restriction on them beyond being a real value as opposed to, imaginary or something like that. Next, we're going to work through a few examples and practice working with this information. What can we actually do with this? So we have example 1. Points U, 3, 0, -1, V, -3, 1, and 2, and W, 4, 7, and -1 lie in a plane. Find the vector and parametric equations of the plane. And if we were to sketch these quickly, we can see that U, V, and W, or we can visualize. And so let's label. U is at 3, 0, -1. V is at -3, 1, and 2. And W is located at 4, 7, and -1. And remember, to define a plane, we need a point and two vectors. So I can use point U. So what do I need to define my plane? I need a position or a position vector or a point. So we're going to use U. And we need two direction vectors. So our two direction vectors are going to be my UW vector and my UV vector. So let's just list that here for a moment. We need two direction vectors. So I needed a point U and two direction vectors. And remember, they need to be non-collinear. So if I do all my math and it turns out that these vectors are collinear, that's going to be a problem. We're going to need to choose a different direction vector. I don't think we need to worry about that here, but just be aware that that's something to watch out for. Cannot define a plane with two collinear vectors. So my first direction vector, M1, is going to be equal to UV. We know the points, so we know how to find the vector, subtract the x values from each other. Once again, I'm not going to show that work because we've done this many times now. So 3 minus -3, or sorry, -3 minus 3 is -6. 1 minus 0 is 1. And -2 minus -1 is 3. There's our first direction vector and our second direction vector, UW. Once again, take the x component of W, or the x value of W, and minus the x value of U, and so on. So 4 minus 3 is 1. 7 minus 0 is 0. And -1 minus -1 is 0. All right, I have a point and I have two direction vectors. Let's write our equation. So we're going to start with our vector equation. Very similar to what we did with lines. We just have an extra term in there now. So R equals 3, 0, -1, so our starting point, plus, and I'm going to have two parameters. My first parameter is S, and my direction vector, -6, 1, and 3, plus my second direction vector, plus my second parameter, T, and my second direction vector, 1, 7, 0. And remember, this is just a vector equation, not the vector equation. I could have switched these up. I could have defined a different direction vector. I could have labeled my parameters as any letter, A and B. We just kind of use S and T as common notation. So this is one way of representing this plane. Also, don't forget to define our parameters and state that S and T are elements of the real. Next, we're going to find our parametric equations. Remember, it's multiple. It's not parametric equation. It's a parametric equation. So it's an equation for each value, the x, the y, and the z. Like someone asked earlier, we don't really need the squiggle. It can be helpful just personally to keep track of things. Know you're having your x, your y, and your z component, and they all come together to describe the same thing. So that in our case, it's a plane now. But if you don't have the squiggle, that's okay. Our x component. So we're going to look at our x values up here. So our 3 and our s times -6 and our t times 1. So I'm going to have 3 minus 6s plus t. And then the y components to the 0 and the s times 1 and the t times 7. So my y component is going to be equals 1s, or s, plus 7t. And finally, my z component, looking at those z parts there, is going to be -1 plus 3s plus t times 0 is 0t, or 0, so I don't need to write that. And don't forget to define our parameter. S and t are elements of the real. All right, excellent. We've just written or learned how to define a plane in vector form using the vector equation and using parametric equations. It's something new, but it's just a slight step beyond what we've done already in terms of lines, so hopefully it's not too scary for you. All right, let's take a look at example 2. So we've learned how to define a plane. Now let's see if we can answer some things about planes. Does the point -1, 11, 2 lie in the plane described by the following vector equation of a plane? Once again, this will be similar to our work with lines. We're going to need to define our parameters. So we're going to need our parametric equations, and we're going to have to see if all these lines exist on this plane. So what are we going to do? We're going to be testing this point. So we're going to use parametric equations. And just to visualize, we're going to have some plane defined by the vector equation given here. We have some point -1, 11, 2, and we want to see, does this exist somewhere in our plane? Let's find out. The first thing I'm going to do is convert my my vector equation of my plane into the parametric equations. So the x component is going to be -6 plus 3s plus 8t, and the y component is going to be equal to 6 plus 4s minus t, and the z component, again, the squiggle doesn't really matter, but if I'm going to have it, I'd like to be tidy about it. The z component, or the z parametric equation, is -1 plus 0 times s, so I don't need that. It's just a 0 term, minus 3t. Don't forget to define our variables. S and t are element of the real, all real values. Let's start by testing our point. So if we're making, let's see if I can find room to keep track of my steps here. So first step I did was go from vector form of my plane to parametric. Next, I'm going to start by testing my point. Start testing my point. So step 1. Step 2, we are testing -1, 11, 2. Let's start with the x component. So my x component here is -1. So I'm going to set x equal to -1, and then I'm going to write out my parametric equation for x. -6 plus 3s plus 8t. And my y component, I'm going to set that equal to 11. And then the rest of my parametric equation from up here. So 6 plus 4s minus t. And now I just have a series of linear equations that I can solve, or a linear system, which was one of the first things we do in grade 10. So you have seen this before, even if it's been a while and you can't quite remember. So let's start by tidying these equations up. First one, I'm going to collect my like terms. I'm going to bring that -6 over to the other side. And so we're going to end up with 5 equals 3s plus 8t. And here we're going to bring our 6 over and so on. And we're going to end up with 5 equals 4s minus t. And we can label these equations 1 and 2. I just used a 1 and a 2. I think I'll put a box around them just to make those labels distinct from these labels here. And I'll put a box around that so we can talk about it for a moment. So now we're going to solve. I guess I can just describe it here in our steps. So step 3, we're going to solve for s and t using substitution. Oops, too many letters. Substitution or elimination. Everyone's favorite processes. All right, let's take a look. We can do this with substitution pretty easily, actually, because notice that both of these are equal to 5, so we could just set them equal to each other and work from there. What I'm going to do here is elimination first. So let's take our equation 1. So 3, we're solving equation 1, equation 2, and I mean we want to eliminate a variable here, so elimination is a good way to go about this. Let's write our equations. I'm going to rearrange them a little bit, but they're still the same. 3s plus 8t equals 5. And I need some multiple of equation 2 where a variable is going to cancel out. And I want to cancel out my t variable. So see here I have 8t. How can I make the coefficient in front of this be an 8 or a negative 8? I'm going to multiply that whole equation by 8. So for my elimination here, I'm going to have equation 1 and 8 times equation 2. Let's put those values in. So 8 times 4s is 32s minus, so 8 times our negative t is negative 8t, and 8 times 5 is 40. The values that we're canceling out have opposite signs, so we're going to add these together. Technically, you can add or subtract here. Your teacher may have told you to multiply in such a way that you're always going to add them, or they might have just said throw it in there. As long as the magnitude of the coefficient's the same, you can add or subtract, whatever. So you may have seen this done a couple different ways before. Whatever way you are comfortable and familiar with is fine. Let's go through. We're adding, so 3s plus 32s is 35s. 8t plus negative 8t is 0. And 5 plus 40 is 45. All right, now we can quickly rearrange and solve for s. This term is gone. It's just a 0 anyway. It doesn't do anything. S equals 45 divided by 35. And once again, I'm not showing all my steps just because this is stuff that we're familiar with already. And I don't have a lot of room on the screen. We can also put this in lowest terms right away. 45 over 35 is going to be equal to 9 over 7. Now, in order to find our remaining value, we're going to sub this into one of our equations. Remember, it does not matter which of the equations in our linear system we use. I'm going to go ahead and use equation 2. Doesn't really matter which one you choose, though. So we're going to sub our value in sub s equals 9 over 7 into equation 2. And I'm not going to write this as its own step here, just because it's all kind of part of step 3. So sub that value into equation 2. So let's write equation 2. 5 equals 4. Instead of s, we're writing 9 over 7 minus t. Let's go ahead and solve that. So 5 equals 36 over 7 minus t. I need a common denominator to work with this stuff. So instead of 5, I'm going to express it as 35 over 7. Rearranging right away, I'm going to subtract 36 over 7 equals negative t. And once again, I'm skipping steps, but if you want, you can pause and work through this a step at a time, or if you're confused, you can just ask me. But we're going to find out that t is equal to 35 minus 36 is negative 1. I have a negative on both sides, so it becomes positive. So 1 over 7. I'm just going to make a quick note here. Note, there are many paths here. And this one is not the best. All that means is there are different ways of solving this linear system. And so instead of elimination, maybe we should have used substitution. Maybe we should have chosen a different equation to use. There are multiple ways of solving linear systems. And this is not what we're focusing on right now, but just to remind you that we also could have just graphed these two linear equations and looked for like a point of intersection. So we will just note one thing, that what we could have done is we also could have used this equation right away up here where one of the variables is already eliminated. So we could have just used this right away and solved for t. Could have worked with this equation. S is already eliminated. So we could have had our z value from here, because that's the point we're testing. The z value equals -1 minus 3t. Rearrange t equals, etc. So we did not go down that path, but we could have. I'm even the steps I'm writing here, like generally correct, but it's up to you how you want to implement step 3. Whatever works best for you, whatever you're comfortable with. All right, so continuing on, we've defined a value for s. We've defined a value for t. That's great. What do I actually do with those now? Well, now we're going to test z. So step 4, test z. Oops, I want the round one, it's a step. All right, so just like we've done before, I'm going to write my parametric equation. I'm testing with the z value of 2, so I'm going to plug that in for z. So z equals 2, 2 equals -1 minus 3, and I want to test the value of t, which we have here, 1 over 7. And I don't even need the value for s, so like, why did I bother finding it? And that's why this wasn't the best path. I do want to take a step backwards here just for a moment. I don't feel confident saying this is equal when I haven't tested it yet. Once again, different teachers will show you different methods. Some care, some don't. As somebody who's been teaching at Lucas for the last couple of years, they're pretty strict about not writing an equal sign unless you're actually sure of it. So we're going to do a left side, right side check here. So still the same basic idea. We're writing our parametric equation for z from up here. Let's plug in our values. So instead of z, actually I'll just write it. So z is equal, or potentially equal to, or z is equal to -1 minus 3t. We're testing our values, so we're plugging in our z value of 2. So z equals 2. On the right side, -1 minus 3 times t, which we just said was 1 over 7. And let's just carry through. On the right side, -1 minus 3 over 7. Definitely running out of room here. My apologies. -7 over 7 minus 3 over 7 is going to give us -10 over 7. And that most definitely is not equal to 2. 2 does not equal -10 over 7. Left side does not equal right side. Therefore, because this didn't work, because the values we found in our first couple steps did not work, plugging in the values for the s and t, so using our parameter values that we found in the z equation did not give us the z value we were looking for. So I can find these x and y values on the plane, but they do not match with this z value. So let's just state that. Therefore, the point -1, 11 comma 2 does not lie in the plane. Excellent. Let's move on and take a look at number 3. And I'll just zoom out here for a moment so you can see this whole question in all its glory without the watermark. I think this program's pretty good. Reflector, I'll probably buy the paid version, but we'll still trial it for a couple days to make sure. So all our steps are here, and we even have our steps written down the side. Convert our vector to parametric form. Start testing the point. Solve for our parameters using substitution or elimination. And then test Z. And I'll just add one final step, which is the conclusion. Have your concluding statement. Make sure you've actually answered the question instead of just doing a bunch of work with no conclusion, with no final result. Example 3. 2 parallel and distinct lines, so they're not collinear. That's good, I suppose. So parallel and distinct. So just remember, let's visualize. It's going to look like this, as opposed to collinear, which are, you know, the same line or two exact identical lines on top of each other. So 2 parallel and distinct lines, and they're given here. So we have R1, we have our position vector, parameter S, and our direction vector. And our second equation of our line, R2, position vector, parameter, direction vector. And our parameters are defined as element of the real. So 2 parallel and distinct lines given here lie in a plane. Find the equation of the plane. So what do we need in order to find the equation of a plane? Well, we've discussed previously that we're going to need, so finding the equation of the plane, what is required? We're going to need a point, and we're going to need 2 direction vectors or basis vectors. But remember, they must not be collinear. And let's just visualize this situation before we dive into the calculations. So we have a plane, and we have 2 distinct but parallel vectors. So R1 is going to be like here, and R2 is going to be like here. So I can go, you know, back and forth. So if I know a point, I can reach any point. That should be parallel. Adding the direction vector onto there, I can, and scalar multiples, I can reach anywhere along that line, but I can't, you know, go left or right anywhere because there's no in this case, horizontal component to the vector. It only goes one way. All right, let's see what we can do about that. How can I find 2 distinct direction vectors? First of all, let's just look at the direction vectors we're given here and prove what's going on with them. So my M1 is going to be 2, -4, 4. My M2 is going to be -1, 2, -2. And let's just check if they are scalar multiples of each other. So 2, -4, and 4. Once again, I don't want to use an equal sign because I don't know yet. Oh, whatever. Equals some k value of -1, 2, and -2. And we can probably see the pattern right away, but let's just check using our testing method we've talked about before. 2 over -1, we're checking if it's equal to -4 over 2, and if it's equal to 4 over -2. And we can see right away these are all equal to -2, which means k equals -2, which means that our vector here, M1, is equal to -2 times M2. So these are scalar multiples. And therefore, they are parallel and collinear. So we can't use them. So how am I going to define another direction vector here? Well, let's see what we know. In order to find our plane, we need a point. Do I know any points? Yes, I do. So for our point, we'll use this value right here. So my point's going to be at 1, 0, -2. And I need two distinct direction vectors, or basis vectors. So I can use one of them from my equation. So I'm just going to borrow and use M2. And I'm going to use that as my first basis vector for my plane. So I'm just going to label that M pi for plane 1 is equal to, and we're just stealing that one. Actually, sorry, we're going to use M2. So we're just going to use that one. That's fine. It is a vector that lies on the plane. 2 and -2. And for my second direction vector, well, do I know any other points that lie on here? Can I find another point or another direction vector that lies on the plane? Well, sure I can. What if I try going from a known point on the first line to a known point on the second line? And let's just illustrate that for a moment. So I got my plane. It's just hanging out, being all flat and stuff. I got my R1. And I know a point that lies on this line. And I know that point is 1, 0, -2. Where did I get that from? Well, it's right up here in our question. I know one line that lies on that, or one point that lies on that line. What do I know about R2? I know that it's parallel, so the direction vectors are collinear, but they are distinct lines. So even though they're going in the same direction, they're not the same line. So this is R2. Missed my 1 there. This is R1. And do I know any points that lie in R2? Of course I do. I know this point right here. So I'm going to have my second point at -2, 3, and 0. And because those points lie in the lines, and those lines both lie in the plane, each of these points lie in the plane. So if I find a vector going from this point to the other, that vector must lie in the plane. And we can see right away that vector is not collinear, is not going in the same direction as my previous direction vectors. So I can use that as the basis for my second direction vector, my non-collinear, non-parallel direction vector. So let's do some calculations here. Let's find that vector, and we know 2 points. So we're just defining the vector going from that one point to the other, and we can even just call it point A and B, if that makes our life a little easier. This is going to be the basis vector for our plane. So M pi 2 is equal to, subtract the x components. -2 minus 1 is -3. And 3 minus 0 is 3. And 0 minus -2 is 2. And so we can put that information up here with our set of information that we know. And we know this vector here is another vector that lies on our plane. And we already know that it's not collinear. We don't have to do that test because these two lines, R1 and R2, were already collinear. So any line going from one of them to the other cannot also be collinear with that. We don't know if it's 90 degrees or anything. We could test that with the dot product. We don't have to here, just saying that it's possible. But I don't need to test for collinearity right now, so I'm not going to worry about that. All right, we have all our pieces. Let's actually put them together and answer the question. Because the question said, find the equation of the plane. Or find an equation of the plane. So therefore, an equation of this plane is pi for plane. We list one point that lies on the plane, and we'll use our point that we've already selected up here. So 1, 0, -2 plus, and it doesn't matter what we call our parameters. I'm going to call my first parameter A, multiplied by my first basis vector. So -1, 2, -2, plus B times my second basis vector, which coincidentally is right here, or right here. So -3, 3, 2. Move that up so you can actually see it. And we're just about done. Don't forget to define our parameters. We want to indicate that A and B are elements of the real. And there we go. Did we do what the question asked? Let's just triple check. Question said find the equation of the plane, or find an equation of the plane. And we have successfully found an equation of the plane. I should just include this part as part of my answer. We'll just tidy that up real quick. And that looks pretty good to me. Once again, I'll zoom out so we can just get a snapshot of the whole thing. And let's describe our steps. What did we actually do here? Well, step 1, we checked if our direction vectors are collinear. They were, and we already knew they were because it told us that the lines were parallel. So we did our test anyway to make sure. Next, we found another direction vector. So find a non-collinear direction vector. Or basis vector for our plane. And if we already had these at the start of the question, we could go right to step 3. So using 1 point and 2 basis or direction vectors, define the plane. Or in other words, write the equation of the plane. So just to briefly summarize what we did here, and I'll zoom out so you can see the whole question in all its glory. And if you want to pause and write anything down or review the steps, now would be a great moment to do that. Almost done. We have 2 more examples. Let's take a look at example 4. Determine the vector and parametric equations of the plane that contain the line R1, given there, where S is an element of the real, and is parallel to the line R2. And let's make sure we're reading the question carefully. It doesn't say this time that the lines are parallel. It says that the plane is parallel to the line. So if we look at a side view, my line's like here, and my plane is here. If we tried to make it a little more three-dimensional, so this line will not intersect with the plane. But what do we know about that? That tells us something, actually, that if I know a vector, or if I have a direction vector for this line here, that vector is collinear with, or is parallel to any line in the plane. So I can actually use this direction vector here as one of the direction vectors for my plane here. All right, let's take a look at how we're going to put these pieces together and actually answer this question. And I'm actually going to recreate my sketch here just so we have it off to the side to visualize. And because there's a piece that I forgot to put in. So we're going to have our plane, tau. We know that R1 lies in the plane. So I'm going to sketch that accordingly. R1 lies in the plane. And we know it contains the point 3, 5, -1. And then R2 is going to be above our plane, parallel to it, so never intersecting, and it includes the point -2, 0, and 4. So that's great. So I have 2 different lines, and I have 2 different direction vectors, but before I can use them to define a plane, I need to make sure they are not collinear. So I guess step 1, we're going to be check if direction vectors are collinear. So do they have the same slope? Do they travel in the same direction? So let's do our test. Remember, we just look at the quotient of one direction vector over another. So we'll have -2/1, so -2/1, and 1/1, and 8/2. Are those equal? No. The first one is -2. The second one is 1. and the next one is 4. So these are not equal. So if we called this M1 and we called this M2, M1 does not equal some scalar multiple of M2. And that's great. That means we already have two direction vectors that we can use. So what do we need to define our plane? We need two direction vectors and a point. So step 2, use 1 point and 2 direction vectors to define our plane. I still think airplane almost every time I say that. Maybe you're thinking the same thing. All right, so any point that we know lies on the line, well, I can just use this one, right? No, I can't. Make sure we're reading the question carefully before. Both our lines lied in the plane, so it didn't matter which one we chose, but we said that R2 is not in the plane. It's floating up here above the plane. It's parallel to it. So I need to choose my position from R1. This position here from the vector that lies in the plane. So just watch out for that when you're working. So our point is 3, comma 5, comma negative 1. My first basis vector is going to be from the line that lies in the plane. So 1, 1, 2. Oops. And my second basis vector from my plane is my direction vector from R2, because it was parallel to the plane, so it travels in the same direction as the plane, although it doesn't intersect with it. 1, 8. And now we can put all those pieces together. And we were asked to find the vector equation and the parametric equation. Let's start with our vector equation. So pi for plane is equal to our point that lies in the plane plus my first parameter s times my first direction vector or basis vector plus my second parameter t times my second basis or direction vector. And don't forget to define our variables. S and t are elements of the real. So we have successfully found the vector equation. And to finish up, we just have to convert from vector form to parametric form, which is not too bad. We've done this a number of times. It's very similar to what we saw with lines. So my x component, x is equal to 3 plus s minus 2t. Y is equal to 5 plus s plus t. And z is equal to negative 1 plus 2s plus 8t, where s and t are elements of the real. Excellent. Looks pretty good to me. Let's just put a box around that to indicate that it's our conclusion to this question. And as we can see from the diagram here, what happened was we took the direction vector from R2, which we called D2. I didn't call it D2. This is just a note from a textbook, I think. So we took our direction vector from R2. So our direction vector came, from this line here. Because R2 is parallel to the plane, then, and we can just call this D2. Then D2 is the direction vector from the plane that we used, and we used it as our second direction vector along with the direction vector from R1. So R1 was here, we had our direction vector. We saw that these direction vectors were not collinear, and let's just kind of visually confirm that, although it's not really proof. But we can see, well, these certainly don't seem to be matching up, and that's good, because we needed them to be distinct non-parallel vectors. So this is just a quick overview description of what we did already, and kind of what I've already described above. Yeah, we'll leave that in there. Direction vector 1. All right, cool. I'll zoom out once again just to give you the overview, and in case anything was covered by the watermark while you were writing and working through this. Finally, let's take a look at our last example. What else can we do with our newfound skills? Given the parametric equations of the plane, so we have our plane defined here. Very nice. Parametric equations. And let's just quickly, s and t are elements of the real. And if we wanted to make our life a little easier, if you wanted to quickly identify our parametric values, our parameter values here, we can think of this as 4 plus 0s minus t if you find that helpful. What are we asked to do here? We're asked to write the vector equation of this plane and find a vector perpendicular to this plane. How many such vectors are there? Let's take a look. In the first case, we're going to start by converting from our parametric form to our vector form. So once again, I'll write my steps off to the side here. Step 1, we're going to go from parametric to our vector equation. All right. So step 1, r is equal to, and let's give our point. So our point is right here. I'm just going to erase this so we're not looking at two different versions of the z parametric equation. Doesn't really matter though. So our point, so 3, 5, 4, plus my parameter s times my first direction vector. So, factor the s out of there. So we're going to have -1, 1, and 0. And that gives us our first direction vector, plus my parameter t, and my second direction vector here, we're just factoring out that t. So we're going to have 2 and 1 and -1, and that defines our second direction vector m2. And don't forget to define our parameter s and t are elements of the real. All right, cool. We are done number 1. Number 2, we're going to need to find a vector that is perpendicular to m1 and m2. So if we were to draw our sketch, I think I can fit this in here. If I have my plane, tau, and I have my direction vectors that I just defined, or I just found in my, as I wrote the vector equation. So m1 is some vector, -1, 1, 0, and m2 is some vector 2, 1, -1. I need to somehow find a vector that is perpendicular to both of them. So some vector that rises directly out of the plane and punctures through. So you can think of the plane as like a piece of paper, and the pencil is, and the line we're looking for is the pencil that we've stabbed through. So let's write our steps. What are we going to do next? We are going to find a vector perpendicular. I really hope I said perpendicular a moment ago instead of parallel. So we're finding a vector that is perpendicular to m1 and m2. I can't go back and check, but I'm correcting myself now in case I said the wrong thing. So find a vector that is perpendicular to m1 and m2. And do we know any way of doing that? If you're not sure, pause the video for a moment and think, do I have a tool in my toolbox for finding a vector perpendicular to two other vectors? Or if you already know the answer, then congratulations. So pause here if you want to think for a moment. Otherwise, we're going to go ahead and I will tell you that we need a cross product. So step 2, we're going to find the cross product of m1 and m2. So m1 cross m2. Remember, we can use the Miss Spring method. We're going to write out our points. So vector m1 we defined up here. So I'm going to write out my points. -1, 1, 0, -1, 1, 0. And the points for my direction vector m2, 2, 1, -1, 2, 1, -1. So write out our points twice and then chop, chop. Goodbye. Oops. And then crisscross. So let's work through those values together. I better show my work as I go, just so we can keep track. So 1 times -1 minus 1 times 0 is going to be -1. 0 times 2 is 0, minus -1 times -1 is 1. So 0 minus 1 is -1. And negative 1 times 1 is 1, minus 2 times 1 is 2. Negative 1 minus 2 is negative 3. So the cross product here, remember, the cross product is a vector. It is a vector that is perpendicular to each of the vectors we are considering. So my cross product here is negative 1, comma negative 1, comma negative 3. And I'm going to indicate here, is this equal to n? We have talked about n before. Do you remember what it represents? N represents the normal vector. Normal means perpendicular. And that's exactly what we want here. We want the vector perpendicular to the plane. We want the normal vector. So we say that the point, or the vector negative 1, negative 1, negative 3, so that vector is normal to the plane. Now we need to test it. How do we know if we are on the right track here? So the final thing we want to consider is how are we going to prove this? How are we going to prove that this normal vector actually is normal or perpendicular to the plane or perpendicular to our direction or basis vectors of the plane? Once again, if you're not sure, pause and think about it for a moment. Otherwise, I'm going to dive in and tell you that we are going to use the dot product. Remember, dot product is a wonderful test for proving if two vectors are perpendicular. So let's test it. And to test it, we're going to use the dot product. So remember, we want n dot m to be 0. So let's check with our normal vector and our first direction or basis vector. N is negative 1, and negative 3. Just realized I have an extra markup here. Let's erase that to avoid confusion. Dot my m1 vector, which was given up here, negative 1, 1, and 0. And remember, to find dot product, we're finding the product of the x and the y and the z components and adding them together. So negative 1 times negative 1 is 1, and negative 1 times 1 is negative 1, so plus minus 1. And negative 3 times 0 is 0. So my dot product is 0. Therefore, n is perpendicular to m1. So far, so good. Let's test our other vector. Is n, or is the dot product of n and m2 also 0? N is negative 1, negative 1, negative 3. Dot my m2 value from up here, 2, 1, and negative 1. So 2, 1, and negative 1. Find the product of each component here. So negative 2 plus negative 1 plus 3. And that also equals 0. Therefore, n is perpendicular to m2. Looks pretty good to me. So let's write our concluding statement. And let's move this up so you can actually see it. Sorry, it's the last page. I can't move it. I can't keep it up, but you can see it there. So, therefore, the vector, our n vector, our normal vector, negative 1, negative 1, negative 3, is perpendicular to the plane. And we could also use a scalar multiple of this vector. So we could also say or 1, 1, 3, and so on. Once again, let's zoom out. Let's get a view of the whole problem. And let's see if I missed any steps here. I did the parametric to vector equation. I found a vector that was perpendicular using the cross product. And I forgot to write down that we also tested. So step 3, which technically you don't need to do, but I do recommend, was test use dot product to show that n is perpendicular to direction vectors. And remember, it has to be perpendicular to both, because both of them lie in the plane. So if they're in the plane, m1, m2, and somehow it's like perpendicular to this vector, but non-perpendicular to this vector, we have a problem. So if we've done everything right, that won't happen anyway, but just watch out for that. All right, we are now experts on finding the equation of a plane in vector and parametric form. Congratulations, we have some new skills. Let's see in our next video, on our next topic, where we can go from here.